Sad. Yeah, I think you're not alone. The here. I assume it's most of you because of the exam results. They weren't as good as the first exam. The average was forgot 60 something. There were several A's and B's and C's. There were just a whole lot of D's and F's also, unfortunately. So the retake, of course, closes at the end of this class period. So what I'm going to suggest is you'll have the weekend to see the answer key and look at what the correct answers are to see, because we'll be honest, there'll be many questions that some of you will look at it and go, oh, dang it. But the ones that are still confusing, we need to discuss. And so we can do that Monday. I think it'll be more efficient and productive if you guys have had a chance to know what the right answers are first, which you don't yet, as opposed to just going over it right now. Do you feel okay about that? It doesn't help everybody, but friendly reminder, this is one reason I offer to drop the lowest exam. Also, because scheduling, some people you can't make it, and some people just don't do as well on exams. So the good news is, those of you that come to class and you plan on taking every exam, whichever one you bomb the most won't even matter in the end, points wise. So that's a bonus. Yeah. The content will be on the final, but not as in much detail because we cover everything. So. But yes, you still will need to learn this stuff. Oh. No, but I don't know if you noticed, I don't weight the final as heavily as a lot of classes do. It annoyed me to no end when professors would... I had a course where all there was one, just the final. That was like your whole grade. Well, that's just stupid in my mind. Or maybe they had one midterm and the final. You know what I mean? And so again, I set this up that, let's say you didn't take one exam ever. Not the final exam, but the normal exams. You could still pass the class. So if you got a 0 on every test, you could still pass. Or say you didn't do a lick of homework ever, you could still pass the class. The way I have it set up, the way I weight it. But yeah, you're still, some of you are feeling bad. But yeah, so look at those, see what the right answers are, and my explanations. And I did look right before I came into the test Wednesday. Less than a third of the entire class have ever looked at the answer keys to the homework that were on this test. So you didn't even know what the right answers were, let alone my explanations for them. Now, many of you did, but I'm just saying it was a third of the class. My TA tells me no one has ever gone to see her. Went to discuss anything with the teaching assistant. I've had 3 or 4 students come to me all semester. I've had more contact me since Wednesday. we'll meet. I'm just so I want to help you understand this, and we'll try. Okay, I'm going to work even harder on this new unit, obviously going forward. But I still want you to understand this stuff too. I would strongly suggest you not wait until right before the final to try to remember/relearn this. You got many things that are going on in your lives before that happens. So when things are in, you think there's too many terms for the same thing. Well, I was confused. Are you implying impulse and impact are the same thing? Because they're totally not. I'm trying to think where I... Well, see, we can get together, go over the exam, and you can point those out. Because if I'm doing that, shame on me, and I'll change and I can adjust or fix, but I can't think of it now. But
I have a question. Do you do the exam?
yes, yes.
Some of the questions for me, because I am adjusted how you talk, and even I watch your videos, in my head, I know how you talk and how you explain. Some of the questions in the text, they were like somebody else did the questions, not you.
Gotcha. I create many of the questions, but our author, his style, which is why I'm using this and picking questions from him, because those of you that read and study this are familiar with his style as well. I won't lie, he's provided a big old bank of questions. There's questions at the end of each chapter. All the odd ones, the answers are actually in the back, so you can practice. Many of those questions are ones plus more for online on WebAssign that are available for me to choose from. I can adjust them any way I want to. The clicker questions I draw from, the large majority are from that bank. Again, I can adjust them. And so the style is consistent throughout. It's the same style as the checkpoint questions, the little yellow boxes in each chapter. Because I never liked either when, this is how we discuss it, and then you get to the test and it's something completely different. So I'm trying to be consistent with that. And also, too, why many of you are starting to, the first exam wasn't as much, but the second more, you realized, you can ask me questions if you don't understand something, or you didn't know what it meant, or is this the same thing? Do these terms mean the same thing? I've told you, ask me. I usually am more giving of information than I probably should be. But
That's the only thing. And I was very tired. I thought I was the only one who was disturbed.
No, I mean, there were many people, again, that did well, but more people did worse on this exam than the first one, yes. So you're not alone. So those of you that are feeling bad right now, thinking, I can't figure this physics stuff out. I love physics, so yes, I'm biased, but I think hang in there. I know the way my course is structured. I know what else I'm teaching. And for crying out loud, we did discuss the special theory of relativity. Kudos to you. I mean, that's not an easy subject just in its own right. So we'll carry on, learn some more stuff. You're not going to remember, you don't remember 100% of everything that I throw at you in this course. I didn't either when I was a student. So, special case. Go look at the exam 2, because after 1 o'clock, the retake's done, and you can view the answers and my explanations. Compare what you were thinking. Bring those questions, and let's see if we can resolve some things Monday or onward. So I don't want you to be confused. This is your class. It's for you guys to learn this stuff. So help me help you. Okay. Oh, yes?
Are you allowed to change the exams around at all?
What do you mean by changing them around?
Adjust them so you don't have to say, but if there's none of these, is that answer? Those are...
Oh, and one of the options is none of the above, or none.
You're trying to figure them all out, and it's like, wait a minute.
Oh, I meant those. The idea is more that it's, you have to read the other, and it's like realize that it's none of those, that none of those apply. Sometimes you can, multiple choice, we won't lie, you can guess. When there's none of the above, guessing isn't as advantageous to you. Because some people are like, I don't know what that is, but I know this one, I know this, I'm not sure. And if you only half know some concept, those are a lot harder questions. So those are more to gauge those that are understanding it more completely. So yeah, I do ask a few of those. Tests do try to, it's a test. Let's see what you got. How many are getting all this? And I know some professors have the philosophy that, make it really hard so that nobody can get 100%, because they want to know that those people that are really getting this and understanding it will get up there. But if you make it too easy, all of them, too many get up there, and then they can't tell if they're really learning it, or... I don't do that. I don't intentionally try to do that. And I honestly do not try to pick harder questions for the exam. before we started the class, I went over what my questions in the bank, and I decided, okay, I want this one for the homework. I want this one for a test. And I've even switched, like, oh, that's going to take too long on the test. Let's put it on the homework when they have more time to think about it and understand it. I'll ask this one on the test. When in doubt, I do that. But I don't sit there and go, okay, now that we've taught it all, and they're having trouble with this one, I'm going to put that on the test. That probably doesn't make you feel any better either, but that's what I do. I at least think it's helpful if you know what I'm thinking instead of just springing it all on you. Well, we are on a new unit. The next chapters before the third exam will be chapters 13, 14, 15, and 16. So no skipping. 13, 14, 15, and 16. 13 and 14 are on fluids. 13 is about liquids, and 14 is about gases. Both of those are a fluid. Usually when we think of fluid, we just think water, things that flow. But all liquids, blood, glycerin, maple syrup, those are liquids. But gases also, like air, oxygen, nitrogen, those are fluids too because they can flow. So 13 and 14 are on fluids, density, buoyancy, pressure. Then 15 and 16 are about heat and thermodynamics. And historically, they thought of heat as a fluid, like it was this thermal energy that would flow from one object to another. And we'll learn heat's a lot like work. You have forms of energy, kinetic energy and potential energy, and they transfer. And by doing work, you can change forms or relocate where the energy's at for position by raising something up. Whoosh. I just did work, and now has more potential energy. So work is a way to transfer energy. Heat is a way to transfer energy between a hot object and a cold object. And we'll talk about ways to transfer that energy. That's the next unit. So we start with chapter 13 on liquids. And the first concept is pressure. Let me go ahead and write that. So pressure. And it's physics, I'm sorry, it's a P. But it's a capital P, where momentum was usually a lowercase p. And if you're ever confused, just ask me. Pressure is a force over an area. That's it. That's our guide to thinking for this equation, this concept. We've dealt with forces before. You know what that is. It's measured in newtons or pounds. We use newtons. And it makes sense. That's how I like to make the connection. Here's a fluid, a bunch of water. It's made up of a bunch of particles. They have weight. They have mass. Gravity's pulling on them. So that they have a weight. But there's too many of them to deal with. We could add up all of the molecules and atoms, figure out their mass, multiply by gravity, and we get its weight, right? Friendly reminder, mass times acceleration due to gravity. And then we could figure out the area that it's acting over and solve all these problems. It just gets very tedious when you're dealing with a whole bunch of little microscopic atoms and molecules or particles. So, pressure. We're going to start using that. We're just going to sum up the force. So like in this case, all this weight. I don't care how many atoms are there. And it's over a certain area. Now, you're more familiar with this than you realize. It's the idea, this thing weighs, I wrote it down. There it is. Sorry, some of you probably can't see through this. Put it back up if we get to it. This weighs 11.5 newtons. And if I put it on this side, I've measured the distance. The area, you guys remember how to find area? Length times width. So that's all I did. The area is 0.018 square meters, because it's going to be meters by meters, a length times a length. So to figure out the pressure this exerts on the table, you just plug it in. It's this force, 11.5, divided by the area. And so we don't have to get our calculators out. That comes out to be 639 newtons per square meter. And like Newton kind of summed up many units for force. Remember, it was a kilogram meter per second squared. Kilogram meter per second squared. We call it a Newton. Pressure has a similar one called a Pascal, and it's represented with PA. Blaise Pascal was a scientist who worked on this relationship. So we would say the pressure the table feels from this block is 639 pascals. Other units of force you might have heard of are millimeters of mercury, inches of water, bar, hectobar. There seems to be a lot for those. Torr, millibar, dynes per square centimeter. Well, that's a bar. Anyway, we'll deal with Pascal because there's too many of those. Well, what if I turn this on its... What's that?
Which one is most common?
Pascal. Well, which one's most common? In the medical field, millimeters of mercury is. How many of you know your blood pressure? Seriously, how many of you know what your blood pressure is? Shame on you. That's one of the most critical numbers of your health. You should be aware of your blood pressure to know whether it's too high or too low, even at this age. Yes, it matters. Well, they measure that in millimeters of mercury. There's two numbers, and I won't get into what they are, but it's the pressure needed that your heart's working or to get blood out of your heart or in your arteries. But they measured in millimeters of mercury. So that's common in the medical field. The weather field uses, that one varies. They usually use hectobar or inches of water, because historically they did that with the weather and atmospheric pressure. We're going to deal with Pascal. In the science world, Pascal is by far the most common. Anywhere outside of those two, it's Pascal.
What do they use for diving?
I don't know. I'm not as familiar with the field to know what unit they use. But they might sum it up as atmospheres. Some people just sum it up as atmosphere. And we're going to learn in chapter 14 in two more lectures. The air in this room has mass. So it has a weight, just like the fluid of water. And it's pushing down on us on a certain area, right? You have a certain area and all this air is pushing on it. So the air exerts a force over an area and exerts pressure on us. We call that atmospheric pressure. And we don't think we feel pressure, but there is. And that's called 1 atmosphere. And that is, 1 atmosphere is, I should know this. But lest I say it wrong, there it is. 101,300 pascals, to give you an idea. So over 100,000 pascals is 1 atmosphere. As you dive underwater, not only do you have the weight of the air pushing on you, 1 atmosphere, when you go under the water, you have the weight of the water that's above you pushing on you also. And so divers might very well say, oh, I've gone down to 2 atmospheres, meaning there's enough water on top of me to equal the same as what we're used to right now. And so they would actually be feeling 2 atmospheres of pressure. I believe that's about 10 meters down. So if you went roughly 20 meters down, you'd feel that 1 atmosphere from the air and 2 atmospheres from the water. So the scuba diver would be feeling 3 atmospheres. Does that make sense? So yeah, you'll hear many of these. This one will make more... Well, let's just do that one now. Here's my demo for it. If these represent particles, each of them has a mass. They're separated by springs so they can... And they settle to this position. So you guys are good scientists. What do you observe? Bingo. That's usually what most people notice first. They're more squished at the bottom. Why? What's that? And they're more spaced out here. Well, this one has to support who? Just this guy. Just his weight. This one has to support 2. This one has to support all of them. So this is my visual for this pressure, especially atmospheric pressure, or pressure when you go underwater. So all the air above us, you can think of these. And we're right here. So what pressure do we feel? All of their weight, force, over our area. That's how it's found. And if you dive deeper underwater, I think you guys know the pressure increases probably already. Your ears can start to pop, or there's pressure anyway. That's because the added pressure of the liquid molecules are adding on to you and pushing on your area. And so your eardrum is starting to get pushed in because the pressure out here is more than the pressure inside your ear. And when there's a difference in pressure, that's when we notice things. I'll repeat that. That's kind of key to a lot of things. When there's a difference in pressure, that's when we notice things. Our whole weather on the planet is driven by differences in pressure. Wind, it's a fluid. It's air. It wouldn't move if the pressure here was the same as the pressure here. Because the force on this acting on this area would be the same as the force acting on this area. But if this pressure increases, now the fluid will start to move from high pressure to low pressure. Just like your eardrum would as you go down. High pressure, inside, low pressure. Or if you go up in an airplane. That's where my ears don't like it. We got atmospheric pressure inside our head right now. Well, it's atmospheric pressure outside our head, so we're normal. You go up. The higher up you go in the atmosphere, that's like, look, there's less pressure because there's less atmosphere on top of you. So when you're higher up, like on the top of a mountain, the pressure outside drops. But if your ears haven't adjusted yet, the pressure inside's higher, and your eardrum will start to sway the other way, outward. And that hurts some people. Yes?
Does the atmosphere kind of provide its own pressure as well? Because, so you had that layer and the particles space out more when you get closer to the atmosphere. Does the atmosphere layer itself, is that condensed or like how does it look like?
What happens in the atmosphere? Yeah, in chapter 14, it discusses that. It has pictures. So you got the Earth, and to scale, our entire atmosphere is about this thick. So realize it's relatively thin compared to the Earth itself. But since that's hard to talk about, we'll go ground. And let's say, that's outer space. And so we have all this air. Yes, it looks like this. The particles up top, there's less pressure up here. Because there's less air up there. And down here, it's more. I think what also you're getting to is density, which is the next thing I wanted to talk about. Down here, it's more dense as well. D for density. There are just generally less particles up here too. So two things are going on. And they affect each other. You guys remember density from high school or wherever? I learned this one from one of my daughter's teachers. I just love density. Because density is mass divided by volume. Well, if it helps you remember it, I don't know. So it's mass over volume. We'll use a capital V for that to try to differentiate between velocity. But again, if you get confused, just ask me. Oh, I never...
What's the proverbial top of the lid of the atmosphere? What keeps those top ones there?
Oh yeah, why doesn't it just go away? I think you know that. Let's say you're up here. What would happen? Bingo. Why? You'd fall. Gravity. They feel gravity too because they have a mass. And so gravity keeps our atmosphere shielding our planet. Some of them do escape. If they get enough energy, they get hot enough and have enough energy, kinetic energy, they could escape. But on the whole, doesn't. It's one of the main reasons the moon doesn't have an atmosphere. Doesn't have enough gravity to keep it there. There are other factors. So whenever somebody's watching this in astronomy, but it's a big factor. So yeah, force of gravity. We take them for granted, air, but it does have mass. It is an object. And all the laws of Newton we've learned apply to them. Again, we're just not going to deal with individual particles. We're going to deal with pressure. It's easier to do them kind of in bulk. So density is mass over volume. So up till now, we've dealt with how much mass you have, the weight or whatever. Well, you can think, too, how much matter is crammed into a certain amount of space. Let's go back to this one. You can see that on here, these at the bottom are crammed in closer together. So there's more mass in the same amount of space as there is up here. So like here maybe only 3 fit, but down here 4 fit. So we'd say this is more dense. So you can either be more dense because you have more mass in the same volume, or you can take the same mass and spread it out and have, I guess that would be less dense then. Or the same mass and shrink it, squish it into a tighter space. That would increase the density.
So I keep talking about the atmosphere, but
go ahead.
It kind of seems like
I don't mind that you talk about the atmosphere because in my mind, everything we're going to learn about the liquids in Chapter 13 applies to gases in 14. So
it seems like the atmosphere, I just try to understand how it's a protective layer, because if it's less dense, then it seems like it needs to be able to penetrate it more quickly because it has less mass and volume.
well, it is less dense, which means it is easier to penetrate and get through. I mean, it's easier to go like this. I can move right through the atmosphere, where I can't move through this because it's more dense. But there's a whole lot of atmosphere. What it means is we could figure it out. Let's do that. There's a value. Well, I'll just rewrite it. Give you an idea. All right, a square inch. If the area were 1 square inch, because we can picture that, right? And we know what atmospheric pressure is. This is 1 atmosphere, which is that many pascals. So if you plug in this many pascals for pressure and multiply it by area, that would tell you how much force is acting on you from the air on top of you. You want to know what it is? I'll show you. At sea level, it's 14.7 pounds per square inch. Pounds per square inch is another unit. But that's the one most people are familiar with when I say that. PSI, pounds per square inch. So this force for the atmosphere is 14.7 pounds, see, force per square inch area. And so you can visualize this. One atmospheric pressure this weighs 14.7 pounds. But it's not acting over a square inch. Since you asked, set your hand down there on the table. You go ahead and balance. That's 14.7 pounds. The weight doesn't change. But I can change the pressure. See, he's acting over several square inches right now. This end is a square inch. So now you're getting all 14.7 pounds on a square inch. That's what atmospheric pressure feels like.
Okay. So that compared to outer space provides that protection.
Yeah, it's protection from outer space. And we don't notice this, but that's what it's like. So, next time you're feeling down or feeling weak, a quarter, that's about a square inch. Let's say it weighs 14.7 pounds. Put that on your arm. And if you want to feel this afterwards, just go right ahead. That's on 1 square inch. Now take a second 14.7 pound quarter, put it right next to the first one. Cover your entire body with 14.7 pound quarters. Every square inch feels 14.7 pounds, pushing on it. There's air here, it's pushing. Why? Because of all the air on top of it, 14.7 pounds worth. And over here, and right here, and over here. So, see? Next time you're feeling weak, remember that. Why don't you just implode from all that pressure? Because that's acting on you right now. It must be equal. There's no difference. There must be a comparable pressure pushing outward. Our lungs are full of air. Our bones and muscle structure withstand that. And I'm going to do a demo later to let you feel the difference if I got rid of some of the air. It's kind of fun. But good question. That helps us visualize the difference of pressure. So again, it's this. This weight over this area, or same weight, half the area. What happened to the pressure? It went up. How much? Twice. This is half the area. You can kind of approximate there. You can see you got 2 of them. So that's spread over twice the area, so it's half the pressure. Put it over half the area, it's twice the pressure. But we didn't change the mass, we didn't change the weight, we didn't change the density. I did change the position. And the gravitational potential energy would have changed. This is a little lower on average, this is a little higher. So yeah, there is a difference in gravitational potential energy. See? You're connecting this stuff. Well, this is good. We covered stuff. Wasn't how I was going to do it, but it doesn't matter. It's all good. I want to check you with density, because I found that if you're confused with density, so get your clickers out, the rest of this stuff doesn't make sense. So, I got a few questions for you that I made up myself this time. See how dense you are. I like that. Sorry. Not exactly, but... You know, it helps if I hit power, doesn't it? Okay, there we go. So it's just 4 questions. These are actually in chapter 12 that I got these from. They're a checkpoint in chapter 12 when it's discussing solids. That's where they introduce density. We're not covering chapter 12, but it still applies with liquids. And so I've adapted them for us and put them on here. I'm hoping they're fairly easy, but we'll all be on the same wavelength by the time we get done here. So, if you didn't know, water expands. That means it increases its volume when it freezes. Given that, I just want to say, okay, who's more dense, water or ice? Or is there a difference? Because it's the same stuff. This is strictly a density concept. Density is mass divided by volume. If it helps, and I know the author refers to it while you guys are thinking, he often calls density kind of like a... scratch that. Never mind, I don't want to go there lest it confuses somebody yet. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you think water is more dense. You're correct. Look at it this way. If you took water and froze it, would it take up more space or less space? More. The volume would be bigger because ice expands. Water expands when it turns into ice. It freezes. So you didn't change the mass. If you had the same amount of water, you have the same amount of ice. It's just it's taking up more space now. You've increased the volume. So that makes it less dense. Questions? Yes?
So if you had like an iced beverage and it had ice in it, and you fill it all the way up, when the ice melts, will the level be lower?
That's a great question. You got a drink full of ice, fill it up, whatever. So let's say it's full to the brim and you got ice floating in the top there. When the ice melts, will it overflow?
No, will it be lower since ice is more dense?
Oh, will it be lower?
So
Point is, will it change its level?
more volume. Yeah, there you go.
Yeah, I'm not going to give you the answer to that one yet. I want you to think about that. Because I want to give you some more physics first so that you have the tools to answer that. And we haven't gotten to everything yet because more than one thing's happening there. But just from ice melting, it will take up less space. And so from that regard, it should go down. One little clue is ice doesn't float completely submerged. So all of it wasn't under the water, and that's going to affect things also. So I'll reserve the real answer from that. But that's a thinking person's question there. Okay. Next question. Which weighs more? Liter of ice, liter of water are the same. A liter is a unit for volume. Your little water bottles you drink out of, those are about a liter. That gives you an idea. Roughly. What's this? Oh, there we go. This is a liter. What weighs more? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh, you guys are split. All right. Talk to your neighbor. Let's see if that changes your minds. Tell your neighbor why you answered what you did and see if it affects anything. Because this was pretty much split. You can vote again if you've discussed and If you still think it's the same answer as you did before, fine, but if you change, go ahead. I'm just curious to see how this pans out. So the caveat here is they're the same volume. A liter of ice, a liter of water. Same volume. That's the given. That's a known.
When I bake, when I bake, I wait because it's the easy way for me to bake. If I have to put ice water in the recipe, I measure the water and freeze the water, and from there I add that to my recipe.
Why do you freeze your water before you add it to the recipe?
Because some recipes they ask for ice.
Oh, yeah, okay. If it asks for ice, yeah, you need to know because the volume could change. So yeah, now you know if you measure water and you figure, oh well, one's ice and it's just going to melt anyway. It's all the same. Yeah, you're putting in a different amount, aren't you?
Yeah, no, I weigh the water, and that is the same thing I use.
Oh, I misunderstood. You meant weigh, as in how much it weighs, not wait, as in being patient. My bad.
No,
I'm sorry.
bad. Sorry.
Okay, go ahead and vote again. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There were more of you last time. One more. Come on. Who hasn't voted? I'm not going to wait. Oh, okay, there you go. Ooh, we changed. A lot more of you think water. You're right. So if water expands when it freezes, ice takes up more space. So picture a liter of ice. Well, if you have that same volume of water, what happens when that ice melts? It takes up less space. So yeah, you had more water. A liter of water would weigh more than a liter of ice. You'd have to start with a bigger volume of ice to have the same amount, matter for the same weight. Questions? Next. Oh, good. This is useful then. This is good. I've had people confused in the past. Lead is like that brick that I had. It's that material. And aluminum is like your pop can, in case you don't know what those are. Density, yes. So you got a certain amount of lead, you got a whole lot more aluminum. Which one has the greater density? I'm not giving you the volume, and it's not necessary to answer this. Here's your clue. What's kilograms a unit of? Mass. Right. So you know the mass. And that's too much. This is to emphasize, mass is different than density. I know, you're going, yeah, if I knew the volume, I would know, right? Well, go for it. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. More of you think lead. You're right. So this was sort of meant to mislead you. There's a whole lot of aluminum there. But aluminum, any amount of aluminum is less dense than any amount of lead. Lead is more dense. It's really dense. That's why that brick was so heavy. Now maybe some of you weren't as familiar with lead, and I apologize for that, but most people really, lead is really dense. Even if you only had 1 ounce of it, it's more dense. There's more mass for that little volume than even if you had 1,000 kilograms of aluminum, which would obviously take up a much bigger volume. So lead, just its substance itself, is more dense than aluminum, period. I have one more, I think. Yeah. So try it again. Similar question, slightly different. This time they're the same material. Yeah.
So with the last question, is say you compact the aluminum, like you're going to compress the aluminum to the same amount of volume.
If you could compress the aluminum,
So yeah, if we compress 1,000 kilograms of aluminum to the same volume as the 100 kilogram brick of lead, they would have.
yeah, you can change materials' density by smushing them. But if you're just thinking of like taking a pop can, and if you're just looking at the amount of aluminum and you crumple it, it's still the same density because it's still aluminum. The only way you could change aluminum's density is to physically change it so it's not aluminum anymore, which you can do by pushing on it hard enough, but it actually becomes something else because it physically changes its mass per volume ratio. And then your alchemy. Let's do it with the lead because then we can get gold. Anyway. Now, while I'm on that, if you took a pop can and you wanted to look at the density of the pop can as a whole, the pop can takes up a certain amount of volume. Aluminum and air, or the pop inside. Then you crumple it. Now the pop can's density, you can say, has increased. But the aluminum that's in there is still aluminum. And its density hasn't. Where are you at? 10, 9, 8, 7, 6, 5, 4, 3, 2, find the right button, 1, there you go. The same, very good. It's water. Water's water. It just seems tricky because, you got 1,000 kilograms of water. Well, that means it'll take up, let's see the difference there. 10 to 1,000, that's a factor of 100. So there's 100 times more mass. So it'll take up 100 times more space because water's water and it has the same density. Just because you have more of it doesn't change its density. And what do I got? 2 minutes? Okay, that's enough time to do the ones I don't feel like setting up again next time. Let's do this one. Has anybody ever wanted to lie down on a bed of nails? Because today's the day. These are real nails. You have? Oh. No volunteers? I mean, I can lie on. Okay, come on down. The idea here, since we're at, is that these are sharp. If you sat on one nail, that would hurt, right? That's because we're going to take her weight, that's a force, and she's going to spread it, though, over all the area of the nails. If you can get enough area, gets big, then the pressure goes down. So let me show you real fast so you don't hurt yourself. You don't want to just kind of pop down there. See, small area, booty. Kind of lay down all at once. They are sharp, so be careful. And I got a pillow for you.
Oh, nice.
All right. So yeah, just kind of crab walk on there. Great. You're doing great. That's far enough. Probably too far. There you go. Good. Try that. And she's like, Those of you, would you rather get stepped on by someone in high heels?
Oh, this still kind of hurts.
Or snowshoes? Yeah, heels is on a small area. Same weight, force. Now tell them, does that hurt?
Yeah.
But are you bleeding?
No.
Yeah, I never said it was comfortable. You can get up now if you want.
Okay.
Here, wait. Okay, I'll just slide this out from underneath you then. There we go. You're free. Thank you for trying that. The idea is you can do this. And if we got even more nails, it would hurt less. Most people say it doesn't hurt, but it's not comfortable. But one nail would definitely hurt. You would prick yourself. It's the area that changed, not the weight. Thus, pressure increased or decreased. All right, so you can mull those over. Look up Exam 2 retakes questions. We can go over that as well. And have a great weekend.